All right, good morning, everybody. So we're a little bit behind schedule on terms of the syllabus, so we're going to continue on today in chapter 16. We'll have our inverted lecture on Friday, so I think that'll work out all right. Get it over with before spring break. So last time we were talking about ways in which we can make aldehydes and ketones, and we talked about oxidation of alcohols, and we talked about ozonolysis of alkenes, and we talked about the Friedel-Crafts acylation, and we talked about a variety of things there. We also talked about some reduction methods that we can use to prepare aldehydes and ketones. What were we reducing, and what was the reducing agent? Okay, so we can reduce esters to aldehydes using what reagent? Dibol. Yeah, we can use Dibal, right? So diisobutyl aluminum hydride will work quite well if and only if what? Got to keep it cold, right? So we can do that reduction at low temperatures, and we can actually get aldehydes directly from esters using Dibol. Jack also mentioned acid chlorides. What was the reagent that we used to reduce acid chlorides to aldehydes? Pardon? It is a lithium reagent in a way, but what is it? Organocuprates were to give ketones. But what reducing agent would we use? Okay, you're close. Yeah, so it was tri-tert-butoxy lithium aluminum hydride, right? So it's basically lithium aluminum hydride that three of the hydrogens have been replaced by these bulky tert-butoxy groups, right? And so it only has one equivalent of hydrogen, if you will, per mole, and so we can reduce those quite readily. Again, at low temperature. And I also mentioned to you that practically most of the time chemists don't do these types of reactions unless they have a really compelling reason, because they're kind of tricky. And typically what we like to do is just reduce it all the way to the alcohol, either the acid chloride or the ester, and then oxidize it back up to the aldehyde using what? PCC, right? So good. So quite frequently we will use a two-step process as opposed to the one-step process for practical reasons. Another way in which we can make ketones anyway is to react nitriles, so carbon triple bond in, right? So if we react a nitrile with either a Grignard reagent or an alkyl lithium, followed by aqueous workup, we can get a ketone. Okay? So let's see if we can't figure out the mechanism. So let's start with a nitrile, and let's use methyl magnesium bromide. How will this reaction occur to give me a ketone? What's going to be the first step? Okay, this carbon, right, has these weak pi bonds that we can break. And we know that methyl magnesium bromide behaves as what? A nucleophile. Behaves as CH3 minus, right? So we can think of it in that way. It's going to attack, and it's going to do what? Break one of the pi bonds, right? And we end up getting our R group there, a carbon, double bond nitrogen, methyl. We've got magnesium bromide plus, and what's going to be the charge here? Minus. Okay? So everything's happy. Is that a ketone? It is not. Can it do any further chemistry? Not yet. Grignard cannot come in and attack this again because having a nitrogen with two negative charges on it, not good, not stable. So this is going to stick around like this until we do what? It only has one negative charge right now. But it would have to if it got attacked again and those electrons moved up, and that would be unstable. So now what do? We do aqueous workup, right? We throw it into water, maybe a little bit of acid. Always like to have a little acid around. So let's say H plus, H2O. What's going to happen? It's going to get protonated. I've got a strong base, a really good acid now, right? We protonate, and we generate what's called an imine. Is that a ketone? It is not a ketone. So what happens? Where does the oxygen come from? How do I have ketones up there? From the water, right? And so what happens is these things can hydrolyze in the water, same water that we just dumped it in, right? And you can exchange out the nitrogen for an oxygen from water. And today we're going to talk a little bit about mechanisms that will allow you to see this. This is an equilibrium reaction, and we can drive the equilibrium to the left here because ammonia, number one, is a gas, and two, we've dumped in a lot of water. And so the equilibrium is going to lie to the left here, not to the right on this particular, the way I've got it drawn, okay? So we can take nitriles and convert them into ketones by reaction with organometallic reagents. So the number of methods that you have now to make ketones and aldehydes is growing exponentially, right? You've got lots of ways in which we can make aldehydes and ketones. Mechanisms aren't that complicated, but it is something that you have to know. I can take a nitrile to a ketone. I can take an alcohol to a ketone. I can take an alcohol to an aldehyde. These functional group transformations, you need to be working on them in terms of recall. You have to be able to recall these functional group transformations. There's no magic bullet. There's no mnemonic out there that you're going to be able to remember all this stuff. Okay? You have to do the practice and the work to commit it to memory. Okay? So yeah, so here's the mechanism that we just talked about, right? And this imine intermediate undergoes a hydrolysis with the water and gives you the ketone. So the mechanism is exactly the same whether we're talking about Grignards or alkyl lithiums. Most people choose the Grignards for obvious reasons, but alkyl lithiums will also attack nitriles and ultimately give ketones. Okay? So here's a couple of examples. You can start off with butane nitrile. So there's the carbon, triple bond nitrogen. Here we're using phenyl magnesium bromide. Have you all done the Grignard reaction now in the lab? You haven't done that yet? So this is the exact Grignard reagent you all are going to generate, is the phenyl magnesium bromide. This attacks, right, and breaks the weak pi bond, and then upon hydrolysis you end up making this butyrophenone or phenylpropyl ketone, depending on how you want to name it. But likewise, we can also use benzonitrile and propyl lithium or propyl magnesium bromide. They're just showing a different reagent. And you can actually get to the same product through two different routes. You're going to find from now on, there's probably about half a dozen routes to get to the thing that you want to get to. Okay? And that might seem overkill, but chemists need multiple ways in which they can achieve things because complex molecules have other functional groups. Okay? And so sometimes you have to avoid other chemistries that might get in the way, and so having multiple routes to the same thing is actually quite beneficial. Okay? Now, another thing that we can do with aldehydes and ketones is we can hydrate them. You can take a carbonyl group and you can place it in water and you can make what's called a gem-diol. Does anybody know what gem stands for? Geminal. And what does geminal mean? You were thinking about what? Like a gem? Really what it means is that the two alcohols are sharing the same carbon atom. Okay, that's what geminal means. Vicinal is adjacent, right? Geminal is using the same carbon. Okay? What is this similar to that we've already learned? Okay, so when we used KMNO4, we were making a diol, but were we making a gem diol? What were we making? We were making a vicinal diol, right? So we were taking alkenes, KMNO4, and we were making the syn vicinal diols, right? Okay, so we were making two alcohols. We're making two alcohols here. So it is similar, but yet it's different, right? What other reagent did we use to do this reaction? I told you KMNO4 was tricky, but there was another reagent that we learned about. Pardon? Osmium tetroxide will work, yeah, and it's a little more well-behaved. It's a lot more expensive, but it's more well-behaved chemistry, right? What else is this similar to? If I read that reaction, what is it telling me? If I read it from left to right. Is it an addition reaction? Is it a substitution reaction? What kind of reaction is it? It's an addition reaction. It's an addition of what? Say it. Water, right, to make an alcohol. Okay? What is that similar to that we've already learned about? Hydration of what? Alkenes. Yeah, we've learned how to add alkenes. And what's similar? You've got a pi bond between a carbon, and you're making an alcohol, right? By adding water across the alkene. What are we doing here? We've got a pi bond. It just happens to be between a carbon and an oxygen. And we're adding water across that pi bond to make an alcohol. In this case, though, you end up with two alcohols because one of the atoms is already an oxygen, right? This is an equilibrium process. Okay? This happens when you place aldehydes and ketones in water. So if you ever use acetone, which is a ketone, to rinse off your fingernail paint, and you're rinsing your hands off with water, you are forming a little bit of a gem diol when you do that. The equilibrium might lie to the right, or it might lie to the left, depending on the structure of the aldehyde or the ketone. What do we know about aldehydes and ketones? Which one's more reactive? Aldehydes. So if I take an aldehyde in water, would I expect it to form more or less gem diol? More relative to a ketone, right? Ketones should form less gem diol, okay? And so if you think about it, the equilibrium constant, right, K prime, is going to be equal to the concentration of the product, which is the gem diol, over the concentration of the ketone. Remember, we pull water out, and that's why we call this K prime, because it's the equilibrium constant times the concentration of water. Just to refresh my memory, why is it that we can do that arithmetic? Why is it that I can pull water out of the equation and pull it over here and call it something different? Pardon? Actually, it does. Well, yes, sort of. But it does participate. It's a reactant, right? It's not just because it's a liquid. Does the concentration really change? Not at all. So we can actually pull it out and treat it as a constant, okay? Because the concentration of pure water is about what? 55-ish molar, 55 and a half, right? Somewhere in that range. And so if I put a little bit of ketone in a lot of water, did I really change my concentration of water to any appreciable extent? No. So we can actually pull it out because it remains relatively constant. So what does this tell us if we look at this? So what's this aldehyde? That is formaldehyde. And when we place it in water, we get an apparent equilibrium constant of 2 times 10 to the third. So is the equilibrium lying to the left or the right? To the right, and way to the right, right? Almost exclusively to the right, okay? Because that's 2,000, right? For those of you in biology, what is it that we preserve tissues with? Formaldehyde, and you have a solution in water. They don't call it formaldehyde in water. Has anybody ever seen a bottle of it? Pardon? Formalin is what we call it. And it's actually, when they place it in water, it's actually the gem dihydrate. That's why it stays in water. It is in equilibrium with the formaldehyde, and that's why you can preserve tissues with it. Okay, so formaldehyde completely lies more or less to the right. How about acetaldehyde? This is the aldehyde that our liver makes when we drink our beers and our wines and our whiskeys. What about it? Does it lie to the left or to the right? It lies to the right, but just a little bit, right? There's still a lot of aldehyde around, okay? And so if you've ever experienced a hangover, I'm not encouraging it, but I'm just saying if you've ever experienced it, that feeling that you have is because the aldehyde is dehydrating you. That's why you get the headache, because you're being dehydrated, okay? It's making the gym-diol, and that takes water. And that takes water out of your tissues, out of the system. Okay, that's why they tell you if you get a hangover to drink a lot of water, right, to try to rehydrate you. Okay, but the fact that you still have a lot of aldehyde around, these aldehydes are actually quite toxic. They interact with proteins and they modify them and they do things that they shouldn't, and so you can actually reach toxic levels of these things and die by drinking too much. Here's our good friend acetone. That's your fingernail polish remover, right? Notice it has a very low value for the apparent equilibrium constant. So when you pour acetone into water to make fingernail polish remover, does it lie to the left or to the right in terms of the equilibrium? To the left. It's mostly the ketone. There's very little gym dihydrate around. Okay? And so what you'll notice, right, is that we can actually change some of these values a little bit by looking at how things are substituted. So if you notice putting more and bigger bulky groups on an aldehyde, what happens to the equilibrium constant? It drops down, right? And it lies more to the left. However, when I put a lot of electron withdrawing groups, like chlorines, on the alpha carbon, what happens? It increases, right? So it lies to the what?
To the right.
To the right. Why is that? It is electronegative. That's right. So what does that electronegative group do? Why does it make it lie to the right? It is very reactive. Why? Well, it's not going to dissociate in water. It's not like HCl. All right. Which carbon? The alpha carbon, which does what to the carbonyl carbon? Does it partial? So if it's positive, is it going to want to try to get electrons or give them away? Try to get them, right? And so it's going to put a more positive charge on that carbonyl carbon, which means that it's going to be able to be attacked by a nucleophile better or worse? Better. And so the equilibrium is going to lie to the right, okay? So if you want to think about some real numbers, let's look at formaldehyde. We said that that equilibrium constant was 2 times 10 to the third, right? When we place it in water, 99.9% of it is the gym dihydrate. When we take acetaldehyde, the equilibrium constant, or the apparent equilibrium constant, was about 1.3, right? 58% of it is the gym dihydrate product. So for every mole of ethanol that your body metabolizes and oxidizes into acetaldehyde, it gets oxidized and gets reacted with the water to make the gym diol. Okay? Acetone, however, when we place it in water, only about 0.2% of it is actually as the product. It lies up in terms of the equilibrium, right? All right. So let's think about the mechanism. So let's say, let's just take acetaldehyde. Let's use acetaldehyde, and we place it in water. What's the mechanism for forming the gym dihydrate, or the gym diol? What's going to happen? What is it?
The electrons
From oxygen on the water, right?
attack the carbon and break the double bond.
Okay, so we've got a good nucleophile reacting with a electrophile, right? So we have that occurring. We form what's called a tetrahedral intermediate. What am I missing?
A negative charge
And?
and a positive charge on the bottom.
All right. Think about that. Think about that for me. What do I have in there now that seems to be at odds with itself? The charges in between the carbon. Very good. O minus is what, a weak base or a strong base? I've got a strong base and a strong acid. So is it going to stick around? What's going to happen?
They're going to react with each other.
They are, and how are they going to react?
Like one of the hydrogens
You're right.
will protonate the top off.
It does. And what we say is that it's a proton transfer. And I like to draw that as just a little squiggly line, H+. That is a proton transfer. We have a proton going from one part of the molecule to another because we have a strong force to do so. We got these opposite charges that make one part of the molecule a strong acid, and we got another part of, due to the negative charge that makes it a strong base, and those are incompatible with one another. They're going to react. And so you get a proton transfer from here to here. Now, it's complicated because it probably isn't this proton that just jumps over there, although it's possible. It could be that two of these molecules come into contact with one another and they transfer their proton through different molecules. And so that's why I like to just draw the little squiggly line. And in doing so, we just made the gem dihydrate. But this is nothing more than a series of Lewis acid, Lewis base steps. What's the Lewis acid and the Lewis base in the first part? What's the Lewis acid? The carbonyl, the aldehyde. And the Lewis base is the oxygen of water, right? Lewis acid, Lewis base. What's the Lewis acid and Lewis base here?
Acid is the water base.
Yep. And so it's nothing more than a series of Lewis acid, Lewis base reactions. So the mechanism, pretty straightforward, okay? Now, given that this is an aldehyde with an R group, I know that the equilibrium is going to lie slightly to the right. If it was a ketone, I would know that the equilibrium would lie quite a bit to the left, right? You need to have, I don't expect you to know what those equilibrium constants are. What I expect you to know is that, relatively speaking, is a reaction going to lie to the left or to the right, okay? You need to know that. Okay. What drives the reaction here to the right for this? Excess water is one thing. That's Le Chatelier's principle. But there's also a thermodynamic driving force. What is it? That's right. I've exchanged the weak pi bond for two strong sigma bonds, right? So I know the equilibrium is going to lie to the right, okay? Now, we can also do the exact same thing with alcohols. Alcohols are nothing more than organic derivatives of what? Water, right? So if I can do this with water, heck, I can do this with alcohol, right? And so that's what we're doing here. I take an aldehyde or a ketone. I use an excess of alcohol. I put in a little bit of acid to make this work a little better. It's a catalyst. And I can form an acetal. This is a perfectly reversible reaction. Okay? We call this a gem diol. We call that an acetal. Little different nomenclature. What do you think the mechanism is? Exactly the same as we just did up here. Okay? It's the exact same mechanism. A little bit of acid catalyst makes it go faster. And what that acid catalyst does is it protonates the ketone or the aldehyde and makes it a little more electrophilic. But other than that, the mechanism is exactly the same. Why could this be useful for us? It's reversible, right? So can we put that to use? Okay, that's a little more advanced than what I was thinking about, but that's certainly true. Yeah. So you can make degradable polymers. That's certainly true. A lot of work in that area. Let's suppose that Anna comes in and she's got a molecule that's got an ester and a ketone. And what we want to do is reduce the ester with, let's say, lithium aluminum hydride to the alcohol. And we want to get this product. Okay, maybe she has some reason she wants this product, right? What's the problem? I got to make sure it doesn't react with the ketone, but it will, won't it? If you took this this starting material and you threw it into lithium aluminum hydride, this would actually reduce, and this could actually reduce, right? If we were using something like lithium aluminum hydride, right? If we were using sodium borohydride, the ketone would reduce and the ester would be left alone. But that's not what you want. You want this chemistry to occur, right? So what do we have to do? We have to protect the ketone. And one way to do this is to react the ketone with two equivalents of alcohol and make an acetal. It no longer has pi bonds, does it? So it can't react with the lithium aluminum hydride. And what is left is the ester. Esters don't react with alcohols to make acetals. And so now we can do the chemistry here and get here. And since this is reversible, right, all I got to do now is dump this into a lot of water and the alcohol comes off. Okay? We're using a special alcohol here. What are we using? It's just a single molecule that has both alcohol groups in it. Instead of using something like methanol, which would have to have 2 moles of methanol, all we need is 1 mole of ethylene glycol. Okay? And so we can form these oops, my battery's almost dead. We can form these 5-membered rings that are nothing more than acetals. Okay? That's all that is. Now it's protected. We do the chemistry we want. She reduces it with lithium aluminum hydride, works it up with a little bit of water, gets the alcohol. Then she puts, probably this water and just adds a little acid to it so that this will come off easy. And she ends up generating the ketone back. Okay? So again, what have we learned about protecting groups? We've learned that they have to be able to go on easy. They have to come off easy. So we need reversible chemistry. This fits that. We've also learned that we can protect alcohols. And now we've learned that we can protect ketones and aldehydes. So we have another protecting group strategy that we can add to our toolbox. Okay? So, how much time do I have? We got plenty of time. And we'll get into some more slide material here in just a moment. But let's think about this. Let's keep it simple. Let's just say we're taking acetone and we want to convert that into the acetal, and we're going to use ethylene glycol and a little bit of acid catalyst. Usually we use para-toluene sulfonic acid, or sometimes we use a little bit of sulfuric acid for this. Works pretty well. Okay? And we can drive the reaction to the right. Of course, one of the byproducts here is water. Okay? And we can drive it to the right how? What do you think, John? How can I drive the reaction to the right? I know this is an equilibrium, but I've drawn it as if it's going to the right. So what must I be doing? There's 2 possibilities. I can shift the equilibrium based on temperature, but I probably can't shift it completely to the right. Pardon? I could take the product out of the system, or I could pull off water. Which one's probably easier? Probably water. You all have used drying agents when you've done chemistry, right? You've used like a little magnesium sulfate. What did that do? Sucks the water out, right? Same thing. I can actually run this reaction with a drying agent in it to actually pull the water out and drive the equilibrium to the right. I can also use a whole lot of alcohol and drive the equilibrium to the right. Probably don't want to do that, though, because the alcohol is a functional group that could cause problems with my other chemistry. So removing the water is probably the easiest thing. This will be one of the most complicated mechanisms you've ever seen. Not really. It's lengthy, but it's not complicated. What's the first step? Pardon? Okay, first thing we do is we protonate the carbonyl, oxygen, with the catalytic amount of acid. What does that do to the oxygen? Puts a positive charge on it, right? Now what happens, Jack? Okay, so now we have one of these oxygens, and it doesn't matter which one, they're the same. We'll attack. Now what happens? I get a proton transfer. Does that make sense? Why doesn't it? There is no negative charge. That's exactly right. So I'm not going to have a proton transfer that leads to a final product. The pKa of this is about the same as the pKa of this, more or less. So what does that tell me about the equilibrium? Is it going to lie to the left or the right? It's neither, probably, right? But it can happen. But once this happens, what do I have? What can happen now? I've got a good leaving group. We've learned that water can be a good leaving group, right? How does it leave? Okay, I could leave and generate a carbocation, but there's another way that it can leave. It's not really SN2, but it is a kind of 2-ish kind of thing, right? So I've got to have some nucleophile come in and some leaving group leave. What's that nucleophile going to be? On the other alcohol? I can do that on paper. I could push this pair of electrons here and kick that out and form the ring that I need. But that's probably not what's going to happen. Why? Not steric hindrance. Are there any electron pairs that are closer? Absolutely. These are a lot closer and ready to do the chemistry. These are way out there floating around, moving around, zipping around, right? I mean, on the end of that oxygen. So what happens is, well, it doesn't form an epoxide because it's not going to form a 3-membered ring. But it forms something that looks like that. Now what happens? Is oxygen with a positive charge happy? So what can happen? It can break, but does it just break or does a nucleophile attack it? Yeah, so now the other oxygen's electrons come in and attack. Break that pi bond. And I forgot to write in my water. Water's around, right? Because we lost it here. So I should have put plus water. Okay? So now what happens? I'm almost there, right? What do I have to do? I have to deprotonate. I have to get my acid catalyst back. I told you this was just catalytic. I need just a little bit. So where am I going to get my proton back from? Right there. And so how do I get that? The water will attack. Which is acid, so I get my acid back, and I can drive the equilibrium to the right by removing water as the reaction occurs, or adding excess alcohol. Okay? That's probably the longest mechanism we've discussed in this class. but yet it's one of the simplest because it's nothing more than a series of acid-base steps. What's the acid and base in the first step? The acid is the acid and the base is the oxygen, right? Right? The oxygen of the ketone in this case. What's the acid and the base here? The Lewis acid is the carbonyl carbon, right? What's the Lewis base? The alcohol. Okay, and the proton transfer, what's the acid and the base? What's the Lewis acid? It's the proton, right? What's the Lewis base? The OH, right? So here, what's the Lewis acid and the Lewis base? What's accepting the pair of electrons and what's donating them? Okay, so I've got a leaving group, right? Is that going to be a Lewis acid or a Lewis base? Here it's a Lewis acid because it's accepting the pair of electrons, right, and leaving. And this oxygen's functioning as the nucleophile, so it's kind of the Lewis base, right? So we got Lewis acid, Lewis base. What's the Lewis acid here? Okay, yeah, or the carbonyl carbon. It's being attacked by the nucleophile, right? So we have a Lewis acid, we have a Lewis base. We have a Lewis acid, we have a Lewis base. It's nothing more than a series of Lewis acid, Lewis base steps, right? So you'll remember a while back, probably in 255, I told you that 90-some-odd% of all organic chemistry is nothing more than a series of Lewis acid, Lewis base steps. Okay? It just so happens that we have 1, 2, 3, 4, 5, 6 steps to go through here. But they are all a series of Lewis acid, Lewis base steps. Again, if you can identify Lewis acids and Lewis bases, you can work your way through these types of mechanisms pretty easily. Is there a question? Did I see a hand go up? No. Chapter number is not important here. It's from an old book. We are going to introduce a reaction called the Wittig reaction. The Wittig reaction allows us to convert a carbon-oxygen double bond into a carbon-carbon double bond. It's a very powerful reaction. It's used a lot. And let's just imagine we have cyclohexanone, and I want to convert that into this alkene. Well, I can do that with the Wittig reaction, and we're going to get into that. But if I gave you a take-home quiz tonight and told you to work on it, and you didn't know anything about the Wittig reaction, what tools do you have in your toolbox that would allow you to do this type of reaction right now? All right, so maybe we can use a Grignard reagent, right? We know how to make carbon-carbon bonds with Grignards. I had a student a few years ago who said, if in doubt, use a Grignard. It's not completely true, but it seems to be kind of a good approach, right? So I know that if I take a Grignard, something like methyl magnesium bromide, what am I going to get? A ketone plus a Grignard gives a what? Gives me a tertiary alcohol, right? Is that what I want? No. But what have I done that is similar to what I want? I formed a carbon-carbon bond between the carbonyl carbon and some other carbon, right? Which is what I want here. I just need a double bond. So how do I take this tertiary alcohol and make that? I can remove water. I can dehydrate. And how would I do that? What reagent would I use? I could use sulfuric acid. I could use phosphoric acid. I could use any of those dehydrating acids that we learned about. All seems well and good. Lo and behold, I get the product, but I've got a problem. What's the problem? Is that the only product I'm going to get? Nope. What's the other product that I'll get? Well, I'm going to get yes. The other organic product. Let me be a little more specific. Which one's going to be the major product?
That one.
That's going to be the major product, probably about 95 to 5. You going to keep your job at your company? Nope. You're going to lose it, right? Because you just made what the boss don't want, right? They want this, and you made it as the minor product. You spent a lot of money, and you made something that isn't going to get you your promotion, okay? Why is that? Whose rule? Rules here. Markovnikov's rule is all about additions to alkenes, right? Zaitsev's rule, right? And Zaitsev's rule tells us what? Yeah, we're going to take the hydrogen from the carbon atom, the alpha carbon that has the fewest hydrogens. And that would be these hydrogens, not these hydrogens, right? And I need to take this hydrogen to get this product. So the way in which you know how to make these types of things right now is going to fail you. But it turns out we're lucky. We've got this reaction called the Wittig reaction, which allows us to replace a carbon-oxygen bond with a carbon-carbon bond without having to worry about Zaitsev's rule. Okay? And so the Wittig reaction takes an aldehyde or a ketone plus what we call a Wittig reagent. Notice it's got a carbanion and a phosphorus positively charged. These are next to one another. These are called ylids. Okay, it's how we call them. And what happened? This carbon replaces that oxygen. It's just that simple. Have I drawn it as an equilibrium reaction? I have not. Can you tell me why it is not an equilibrium reaction? Technically, I can go back, but why can't I go back here? On paper, I can draw it in the reverse, but why is it going all the way to the right? I'm using just 1 mole of ketone or aldehyde, and I'm using just 1 mole of the Wittig reagent. So it's not a Le Chatelier's principle issue. Why is it that the equilibrium lies to the right? Uh-huh. Well, that's partially true. So it does have something to do with the triphenylphosphine oxide, but it's not sterics. It is more stable, but why is it more stable? That's true. So that's part of it. The aromatic ring, the phosphines, the phenyl groups on the phosphine, but it has that in the starting material too. So that doesn't explain it.
Not a negative carbon.
That's true.
Carbanion.
What do you all know about the phosphorus-oxygen bond? Is it strong or is it weak?
Strong.
It's strong. It's one of the strongest bonds we know of. How do you all know that? DNA. Because the phosphorus backbone in DNA is really strong. We know that those phosphorus-oxygen bonds have to be strong, right? And so it's the strength of that phosphorus-oxygen double bond that drives this reaction to the right, okay? Is this reaction atom economical? If you want to make an alkene, is this the way to go on an industrial scale? But it's pretty big. I got 3 benzene rings, a phosphorus atom, and a bunch of other stuff, right? It turns out that triphenylphosphine oxide has a lot of mass to it, and it's the waste product. So even though this is a really good reaction on a laboratory scale, industrially they are trying to find ways to get around it. Because the triphenylphosphine oxide, that phosphorus-oxygen bond is so stable, it's hard to reuse it for anything. It ends up being put into, they end up incinerating it, which isn't a good idea, right? And so it's not a great reaction industrially, but it is a well-behaved reaction in terms of making carbon-carbon double bonds. And on a laboratory scale, I used the Wittig reaction just about every day when I was a postdoc at Vanderbilt. I needed to make carbon-carbon double bonds. And I knew that I could take a Wittig reagent, an aldehyde or a ketone, mix them together, come back from lunch, and my product was there. It was one of the best reactions ever. You all will actually do a Wittig reaction in lab, and you can't mess it up. Well, I suppose you can, but it's kind of hard to mess up. Okay? You can mess it up. You can mess it up. Okay? So here's some more examples. Here we have an aldehyde. Notice we're using an ylide here that just has 2 hydrogens. Okay? It's just going to replace the oxygen with the carbon. Here we have an ylide where the carbon with the negative charge has both a hydrogen and a methyl group. These guys just come along for the ride, and I form this alkene. Find the oxygen of the aldehyde or the ketone and replace it with the carbon of the ylide. That's all you have to do. It is that well behaved. You don't have to worry about rearrangements of carbocations. You don't have to worry about Zaitsev's rule. It's easy to do. Okay? You need to have this one certainly committed to memory. All right, we are going to finish up with this on Friday. I'm going to spend probably 15, 20 minutes finishing this up on Friday, and then we'll get in on the inverted lecture. So come prepared, having read the rest of chapter 16. And I will see you all on Friday.